Hello, welcome to ERTH413 Geological Data Analysis. I'm Garrett Ito, and this is the very first lecture of the class, and we'll be covering section 1.1.1 of Paul Wessel's notes, and that will be the main textbook, so to speak, of our class here today. So the three topics we're going to cover today, or in this video, are different data types, different classifications of data types. We'll cover the concepts of signal versus noise, and then we'll cover concepts of accuracy versus precision. So there, I guess you can divide data into two main classes, whether they're discrete, that is, they have discrete values, versus continuous data. So talking about discrete data, I guess in approximate order of data quality, we'll start off with nominal data. Nominal data, comes from the Latin root meaning name, is basically a way of categorizing or classifying information. So there's nothing quantitative about these data. It simply classifies different I guess properties or that you would observe. And so one example is you would classify different species of foraminifera, which I show here in this left diagram. Oops, sorry about that. Another type of classification or nominal data are different rock types, and here I show 4 different types of peridotite. Okay, so that's nominal data. Moving on to ordinal data. Ordinal data is a form of classification in which order has meaning. It's it's ranked in a certain order that has significance. And some examples of that are, for example, in stratigraphy, we classify different stratigraphic sequences in order in which they were deposited. So, for example, the Pliocene, you may see a Pliocene layer below a Pleistocene layer. They're ordered because the Pliocene layer was deposited prior to the Pleistocene, but there's no real quantitative values associated, associated with those names in particular. There are dates associated with those, but those are different types of data than the classifications themselves. Another example is Mohs hardness scale for rock types, and that's a classification in which the lowest hardness is 1, corresponding to talc, and the hardness increases. It's ordered, but there's no real meaning between these different numbers, and it increases up to a hardness of 1 for diamond. And then the last type of discrete data, which is the most quantitative, so to speak, is integer data, or I should say counts, and those are made up of integer quantities. So these are, again, this would be a count of discrete objects, events, or other features that you're looking at. Okay, so we've covered discrete data. Now we'll move on to different types of continuous data. I guess the lowest level of accuracy for continuous data is interval data. Okay, interval data, the values are ranked, and they make use of real numbers, and the difference between the values are constant and have quantitative meaning. But the ratios of numbers do not have real significance, do not have real meaning. So a nice example of interval data is temperature when measured in degrees Celsius and Fahrenheit. 20 degrees C is definitely cooler than 100 degrees C. 21 degrees C is the same temperature difference as 22 degrees C, but there's no meaning in the ratio of 100 to 200 degrees C. 100 degrees C is not 5 times hotter, for example, than 20 degrees C. And then finally there's ratio data, and that is a data type that makes full use of real numbers in which it's like interval data, but the ratios do have meaning. And a good example of that is the temperature scale in degrees Kelvin. So in Kelvin, there is an absolute zero, and for example, 500K represents 5 times as much heat as 100K. Okay, and this is a form of data that many geophysicists use, or a lot of data appears in the earth sciences, especially as we're getting more and more quantitative. Okay, another form of continuous data is closed data. These are data that have values only over a specified range, and a simple example of that is just percentages. There's no such thing as, the range goes from 0 to 100%, and there's no such thing as a minus 5%, or you can't get any more, of course, than 100%. And then finally, we have directional data. And directional data is often used in geology, and the unique values span a limited range. So, for example, if you're describing a direction, for example, here, of motion of southern Iceland as recorded by GPS, you would describe that motion in terms of 0 to 360 degrees. Okay, so that's it for different data types. Now I'd like to talk about signal versus noise. And what defines signal versus what defines noise is intimately related to the objectives of the observer. So please write this down in your notes while I type this out. So the definitions of which are closely tied to the objectives of the observer. So let's talk about signal. So what is signal? So it is the part of the data collected that contains the information sought. Okay, so in order to seek, the goals of the observations are to seek a certain type of information, and the signal is that part of the data that contains that relevant information. And this information sought is sometimes defined by a predictable behavior. See if I can type while talking. Predictable behavior, or characteristic. And sometimes it is based on a model. So you can see that, of course, by the definition of signal, you can see how it's closely tied to the objectives of the observer, as I mentioned above. In terms of noise, what is noise? It's simply the part of the data that is not signal. Okay, and that part of the data that is not signal may be due to natural processes or phenomena not explained by the phenomena that is being studied. Or it may be intimately related to the phenomena being studied, but it's not understood, or it's not part of the characteristic behavior that one would use to define the signal. Noise may also be due to measurement errors. The instruments that one would use to make measurements are certainly not perfect, and they're subject to error. And the worst type of error would be an error by someone misusing the instrument. But that's typically, well, we certainly want to eliminate that type of error when making measurements. That would be a bad thing to do when making measurements. But it could be, it could be there when you look at data. So let me just sketch something out for you here to give you a little bit of an intuitive picture of what noise might be. So let's say we're seismologists and we're measuring the motion of the ground as a function of time. And here's our ground motion. And say we're measuring the motion due to a distant earthquake. And the signal we might seek is something that has a relatively certain wavelength characteristic, for example, has a certain onset time and rate of amplitude increase. But in reality, of course, what our instruments measure is something different than sort of the signal we seek. It contains noise due to a variety of different environmental effects or instrument imperfections. Okay, so that's an illustration of signal versus noise. Now let's go over accuracy. Oops, sorry about that. Let's get my pen working here. Accuracy versus precision. And Paul Wessel shows a nice little diagram, but let's expand it just a little bit. So we're going to make a table with 2 rows and 2 columns. And again, I hope you're doing this with your notes. And what changes with columns is precision. So we can have low precision and high precision. And what changes on with the rows is accuracy. And we can have low accuracy and high accuracy. And let's say we're measuring 2 types of data that perhaps are correlated, perhaps not. So we're going to graph our measurements on this X and Y axes, and say the true value of those points is centered right here on this on the origin of that plot. Okay. So of course, precision measures how well a measurement can be repeated. So if the precision is high, we would make a lot of measurements that are very close to each other, very similar. So the precision is high. And the most desirable type of measurement we want to make is where the accuracy is also high. So in that situation, we measure a lot of points near the true value, and that's the most desirable situation. We could have very high precision, but the measurements are inaccurate, meaning that we make a lot of repeat measurements, but they're far from the true value. And this would be the least desirable situation. This could lead to a situation in which we think we have a good estimate, but in fact our measurements are biased, and that's not very desirable. Okay, so in the case of low precision and high accuracy, we make measurements that are centered near the true value, but our precision is low, so the variability in our measurements is high. And of course, if both accuracy and precision are low, we have a large scatter that's not anywhere near our true value. Okay, so that concludes this lecture for ERTH413, and we'll move on to the next topic in the next video.